Hello friends, welcome back to my YouTube channel. So in today's video we will see one more problem of flexibility method, and in previous video we have solved the how to develop the flexibility matrix we have seen. Today we will take a problem. So this is the given problem. Analyze the beam by flexibility method and draw SFD and BMD. So this is the given B continuous beam. And here one more thing is, in question they can ask analysis the beam by force method. Question they can ask in any one of this name. Either it may be flexibility or force method or compatibility method. So our first thing is what we have to do is, first step is to find out the degree of static indeterminacy. That is nothing but ds we need to find. So to find out the ds we have the formula, that is r minus e minus EC. So here R is the number of reactions, E is the equilibrium equations, static equilibrium equation, and EC is nothing but internal hinge. So this thing I have already explained while solving the static indeterminacy. So for more detail you can go through that video. I will give link in the description box. So now we will see here how many number of reactions are there at fixed end. There will be 3. One is vertical, one is movement, and another will be horizontal. And one more thing is, while calculating the flexibility method we need to neglect the horizontal force. That is nothing but axial deformation we need to neglect while calculating the problem by using the flexibility method. So neglect axial deformation while solving the problem by using the flexibility method. So we should not consider the horizontal force here. We need to neglect it. So it means at fixed end there will be 2 reaction takes place, and at in support there is also 2. One is vertical, another is horizontal. So but we need to neglect the axial deformation. So I am considering only vertical. Here also 2. One is vertical, another is horizontal. I am neglecting horizontal deformation, so that I am only taking vertical force. So now see how total number of reactions are 4. 1, 2, 3, 4. So total number of reactions are 4 minus static equilibrium. Number of static equilibrium equation will be 3. Summation of Fy is equal to 0 and summation of all the moment is equal to 0. Another one is summation of Fx is equal to 0. But in case of flexibility we should not consider this one. We should neglect the axial deformation, horizontal deformation. So we need to consider 2. So number of static equilibrium equations is 2. So there is no internal hinge, so EC becomes 0. 4 minus 2 will be 2. So ds is 2. This is how we need to calculate the degree of static indeterminacy. So at D at 2 means what it means is the number of redundant in this structure is 2. So we need to remove it from this. So I am taking we need to select the support to remove this to redundant. So I am first I'll give name to this. This is A support, this is B, this is C, this is D, this is E. So I am taking it as 1 and support B as 2, redundant 2. This is coordinate number 1 and coordinate number 2. So I will write it here. Take the support B and C as redundant and remove it. So I am giving the coordinate number 1 to this support and 2 to this support. So this is our step number 3, and selecting redundant is step number 2. So I will show you here. See here, second step is select a redundant force and remove them to make a structure statically determined. We have did it. And third step is assign the coordinate to the redundant. So I gave name to the redundant. This is 1, this is 2. So our next is 2. So I have drawn the diagram separately. So we need to draw the diagram separately for find outing the each. So this I remove all the loads here. This is called our capital M, and this is diagram will call as the M1, bending moment of coordinate number 1, and this is the bending moment of coordinate number 2. So capital M is our moment. So I will tell you later what it is. And now we need to by using this diagram we'll draw the unit load method table of unit load method. This is our unit load table. So in last video we only solved the M1 and M2 because they didn't ask to analyze the beam. Here they say to analyze. For analyzing we need capital M also for calculation. That's why we need to calculate here. We need to apply the unit load method for also M also. So now we will see how to fill this table. See here, one more thing is, so if you want to calculate from this side to this side, it means left to right, then you need to calculate these reactions. So if you calculate from this side to this, then we need to skip, you can easily skip the calculation of this reaction. To skipping calculation of these reactions, we'll calculate from right side to left side. Only because to skip the calculation of this reaction, I am calculating from right side to left side. So what happens if you calculate from left side to right side? Here fixed support is there, no? We need to calculate the reaction of this support. To skipping the calculation, I am calculating from the right side to left side. So now we'll apply the methods here. First our member is, here we have member, so I'm giving name here also. This is A, B, C, this is D, this is E. From C to E one member, E to B one member, B to D one member, D to E one member. So I will write it all the member here. For C I am taking origin as C, for EB I am taking origin as E, for BD I am taking origin as B, for DA I am taking origin as T. So limit is same, 4 meter everywhere. See, there will be 4 meters, so limit is 0 to 4 only. Here also 0 to 4, 0 to 4, 0 to 4. So M. So when you apply when you cut the section x-axis far away from the origin C at a distance of x. So from here to here is the intensity is 0. So our M becomes 0 because there is no load, no? So when there is load, the value will come here. At the support it has no load, so it becomes 0. Similarly for our M1 diagram, if we cut the section x-axis for C member, if we cut the section x-axis far away from the origin C at a distance of x, here intensity is 1 kilonewton. So it is moving upward. So above the axis we need to take positive. So it is going upside, no? So positive. When you take the 1 into x at a distance of x, so 1x. Similarly for this M2, if you cut the section x-axis far away from the origin C, here also there is no load, M2 becomes 0. Similarly for EB, the origin is E. For EB, the origin is E. So if you cut the section x-axis far away from the origin E at a distance of x, so what happens? Our M will be, here from here to here distance is x, and from here to here there is no load. If there is any load is acting, then we need to take the from here to here total distance. So the load is 12 km load is acting here. From this load to this point, how much is the distance? 12 into x. So it is moving down, no? So the downward we need to take the, which is moving downward, we need to take the negative. So it is moving downward, so 12 into x, minus 12 into x. M will be minus 12x. Similarly for M1, if you cut the section x-axis far away from the origin E at a distance of x, so here one unit load is acting. From here to here, at what distance it is acting, we need to see. So from here to here distance is x, and from here to here distance is 4. So 4 meter. No, we need to take from here to here distance, that is nothing but our x plus this distance 4. So m1 will be x plus 4. So 1 into x plus 4 will be x plus 4. Similarly for m2, if you cut the section x-axis far away from the origin here at a distance of x, so what happens here, there is no load, so our m2 becomes 0 here. Similarly for member BD, if you cut the section x-axis far away from the origin B at a distance of x, so here on load is acting 12 kilonewton. At what distance it is acting? From here to here we need to see. So from here to here is distance x, so x plus this distance here to here is 4 meter, so x plus 4. So x plus 4 into this load, that is 12. So 12 is, it is moving down, we need to take the negative, so minus 12 into x plus 4 at a distance of x plus 4 it is present. So we need to take m as minus 12 into x plus 4. Similarly for m1, if we cut the section far away from the origin B at a distance of x, so our m1 will be, see, is there any load? So here 1 kilonewton is acting. So at what distance from here to here it is acting? So from here to here is x, so x plus this distance is here 4. 4 plus 4 is 8. So x plus 4 at a distance of x plus 4 it is acting. So 1 is, it is moving upward, we need to take the positive. So 1 into x plus 8. So 1 into x plus 8 is nothing but x plus 8. Similarly our m2, for m2 also, if you cut the section x is far away from the origin B, so here one unit load is acting upward. So at what distance it is acting from here to here is x, so it is going upward, so it is positive. So at a distance of x it is acting. So we, for our m2 will be x. 1x is nothing but x. Similarly if we see for member DA, the origin is D. If we cut the section, if we cut the x-axis at the distance of x from the origin D, see here one load is acting downward, point load is acting downward. At what distance it is acting? See, 12 into from here to here is the distance x. X plus from here to here distance is 4. So 4 plus 4 is 8. So 12 minus 12 into x plus 8. So we need to take. So our m will be minus 12 x plus 8 into, see here one more load is acting, the point load is acting, it is also acting downward at a distance of x, so minus 20 into x it is acting, so we need to add that. Minus 20 into x. So this is our m, capital M. Now similarly for m1, if you cut the section x-axis far away from the origin D, what happens here? Load is 1 kilometer load is acting here. At what distance it is acting? From here to here is 1 into x plus, from here to here distance x, and here to here is 4 plus 4 plus 4, it becomes 8. So x plus 8 distance it is acting. So our, sorry, it is 12. 4 plus 4 plus 4, it becomes 12. At a distance of x plus 12, this load is acting. So write it here, x plus 12. Similarly for m2, if we cut the section x-axis at a distance of x from the origin D, so here one load is acting. At what distance it is acting? From here to here is x plus this distance is 4 meter. So x plus 4, 1 into x plus 4. So it is moving upward now. We need to take the positive. m2 will be x plus 4. So this is how we need to fill the all the bending moments of corresponding diagram. So we need to draw it for each coordinate. We need to draw the separately diagram. So if the one more coordinate is given in problem, coordinate number 3, then we'll draw the one more diagram of m3, and then here also we need to add the m3. So this is how we need to fill. So next we'll see. Next we need to find the flexibility matrix for this. So this is our formula. So f11, and we need to find by using the formula we have already known. By using this formula we need to find integration of 0 to L m1 square divided by ei into dx. So 1 divided by ei is constant. I am taking it outside. 1 divided by ei. So integration of 0 to 4, our limit is 4, and m1 we need to see. We need to integrate m1 separately for c, and for EB, BD and E for separately. We need to, for each member we need to integrate it. So by using the corresponding limits we have to find the integration. So our for C m1 is 1x, and for BE x plus 4, and for BD x plus 8, and for DA x plus 12 we need to add. For C our m1 will be x square into dx plus integration of 0 to 4. For EB we have the m1 value x plus 4 square dx. Similarly for BD we have x plus 8 m1 x plus 8 whole square into dx. Similarly for DA member we have m1 value x plus 12 whole square into dx. So we need to integrate it by using calc. So add all the values. Integration of 0 to 4 into x square plus integration of 0 to 4 into x plus 4 square plus integration of 0 to 4 into x plus 8 square plus integration of 0 to 4 into x plus 12 whole square. So solve it. So it will come out as 1365.33 for F11. So F11 will be 1365.33 divided by EI. Similarly for F22 we have the formula integration of 0 to L m2 square divided by EI into dx is equal to EI is constant. I am taking it as outside. Integration of 0 to 4, for each member we need to put the moment values. So m2 value for member C is 0, and for this member is 0. We need to add these two only. So for member BD it is x, m2 value is x, so x square dx plus integration of 0 to 4. For DA member the value will be x plus 4 whole square into dx. So now solve it by using calc. So integration of 0 to 4 into x square plus integration of 0 to 4 into x plus 4 square. So now solve it. Our F22 value will be 170.66 for F22. So it will be 170.66 divided by EI. Similarly we need to find for F. Here in formula it is F21 and this is 22. So make it correction. Similarly we need to find for F12 and F21. Formula will be same. Integration of 0 to L here we need to take the moment of first point here, and here also moment of first point. Here first point is 1, now we need to take the moment of 1. Here first point is 2, now we need to take the moment of 2, divided by ei into dx. Ei is constant, I am taking it as outside. Now substitute all the 0 to 4, limit is m1 into m2 value. Here for members C and EB, the value m2 value is 0, so 0 into anything becomes 0. So we need to add only for member BD and DA. This into this into this. We need to do it. X plus 8 into x dx plus integration of 0 to 4 x plus 12 into x plus 4 into dx. So now solve it. So integration of 0 to 4 into x plus 8 into x plus integration of 0 to 4 into x plus 12 into x plus 4. So now solve it. It will come out as 426.66 for 1 2 and 2 1. 426.66 divided by ei. So now fill this matrix. So F11 value we got was 1365.33 and F12 426.66. Here also 426.66 and F22 will be 170.66. 170.66 into 1 divided by ei. I am taking it as outside. This is how we need to find. So our next step will be, so by using this formula we'll find out the reactions. So P, it is nothing but also you can call it as R matrix. So I will write here. P is equal to inverse of delta into dou minus dou matrix minus here also dou L, displacement matrix we need to find. So P will be how much our redundant we have taken. We need to take that much of P value. So I am taking, our redundant is 2 now. We need to take P1 and P2. And our inverse of, we need to do the inverse of delta. So our value is this one. We need to fill here 1365.33 in here 426.66 and 426.66 170.66 we need to take. So I am neglecting here because if you put the ei value 1 it becomes 1. So assume, so ei value is 1, so 1 into 1 becomes 1. Assume ei as 1. Similarly, our this value is yielding value is not given, it becomes 0. In question if they given, then only we need to take this, otherwise we need to ignore that. And our dl is nothing but our matrix of d1 and d2. So our dl equal to the matrix of d1 and d2 displacement. So now we need to find the here d1 and d2 value here. So I will show how to find that. So by using formula d1 is equal to integration of 0 to L. So capital M into M1, moment of first coordinate, moment of M1 and divided by ei into dx. So now we need to fill all the value and ei is constant, take it as outside, integration of 0 to 4 and our M will be, here we need to multiply M into M1. So this into this, this into this, this into this, this into this for corresponding members we need to add. For member C it will be 0 0 into anything become 0. So now we need to see. So integration of 0 to 4, M for member EB will be minus 12 EX into m1 will be x plus 4 into dx, plus similarly 0 to 4 the value of bd will be m for that minus 12 into x plus 4, and m1 will be x plus 8 into dx, plus integration of 0 to 4 into minus 12x plus 8 minus 20 into x, and into x plus 12 dx. So now carefully add these values in calci to get the d1 value. So I will write it for d2 also here only. For d2, integration of 0 to L capital M into M2 divided by EI into dx. 1 divided by EI I am taking constant. For each member I am writing all the value here. 0 to 4. So see here for member C and for EB the value becomes 0 because M2 is 0. 0 into anything will becomes, we need to add only these two. This into this, this into this. So minus 12 into x plus 4 into x dx, plus integration of 0 to 4 into minus 12x plus 8 minus 20x into x plus 12 into dx. So now we are using calci, add it. So integration of 0 to 4 into minus 12 into x into x plus 4 plus integration of 0 to 4 into minus 12 into x plus 4 into x plus 8 plus integration of 0 to 4 into minus 12 into x plus 8 minus 20 x into x plus 12. So now solve it very carefully with the calci. So the answer will come out as 12,714 for d1 value. So d1 will be minus 12,714. I am making it as roundabout 12,720. 720 I am making it. So here also assume EI value as 1, so it becomes 1. And similarly for d2 we'll solve. So integration of 0 to 4 into, so minus 12 into x plus 4 into x plus, so plus integration of 0 to 4 into minus 12 into x plus 8 bracket close minus 20 into x into x plus 12 close the bracket. So it is the x plus 4 not 12. So x plus 4. So this is 4. Don't get confused. X plus 4 I will write here. Wait. X plus 4. So x plus 4. So now solve it. It will come out as minus 400 minus 4,650 for d2 value. So see here it is while entering into the calci it is very important. So bracket are also very important. If you
don't put even a single bracket, then you are not getting the exact answer. So here I have made one mistake here, that's why I got the error there. I forget to put here, close the bracket here, this one here, two bracket will come. So while entering the data very carefully, you need to close the bracket also, then only we need to get the exact answer. If you forget to enter the close the bracket, then also you don't get, you will get the error. If you forget to close the bracket, you will get error while calculating. So it's very important to close the bracket. So I'll find out in the integration in calci. So d2 is minus 4650. So here I am taking 1, so I am not putting here. So assume EI value is equal to 1 here. So now we'll put here, put the d1 d2 value to get the P1 and P2 value. See here inverse is there, we forget here, we need to put inverse sign here. So now I will write it again. So same thing I have written here. So find out the P1 and P2 by using calci. I will show how to calculate this one. And see here, we need to add the mod. Here matrix is number at 6. No, we need to press here 6. So 6. See here matrix A. So now we need to fill the matrix A. For that it is at number 1. No, we need to press 1. And here see our the matrix A is 2 into 2 matrix. So for 2 into 2 at number 5, 2 into 2 matrix is there. We need to press 5 here. So now we'll fill all the values corresponding readings. 1365.33 and 426.66 and 426.66, 170.66. So now we need to, what do is, we need to press here AC here we need to press, then press the shift here, then we need to press the 4, number 4 here. See here we need to go inside the data is at number 2, we need to press the number 2. Then you could see the here all the matrix. Now we need to fill the matrix B. So matrix B, for that we need to press here 2. And here our matrix B is 2 into 1. No? So 2 into 1 matrix is here at number 6. Now we need to press the 6. So now we'll get this matrix. We'll enter this value. So minus 12720 and minus 4650. So now press equal. Then also we have to press the AC. And again we need to press the here shift button. And we need to once again go into the 4, press 4, then you will get like this. See here matrix A is at number 3. No, we need to press the 3. So then see here our matrix A, we need to do the universe of this. No, for that see here you could see the universe sign here. Now press this. See here, now we got the matrix inverse of matrix A. Then we need to add matrix B. So here minus is there no, so I am taking bracket into minus sign is there, so minus into matrix B. So again for matrix B we need to press here shift button, shift, and go inside. Again press the, after shift number 4, see shift again number 4 I press it. See here matrix B is at number 4, or matrix B is there, so we need to press the 4 here. So press 4, see mat B came, so close the bracket. So now press equal button to solve the. So now we got the above one is P1 value and P2 value, the below one is P2 value. So P1 value is 3.66 and our P2 value is 18.09. This is how we need to calculate P1 and P2 by using calci. So our P1 value will be 3.66 and P2 value will be 18.09. P1 and P2 are value nothing but our reactions of coordinate 1 and coordinate 2. So our P1 is nothing but reaction at coordinate 1. This is, we have taken coordinate number 1 no? So this value is 3.66 and P2 is nothing but our coordinate reaction of coordinate 2. So coordinate 2 is here, that is 18.09 kilonewton. This is also kilonewton. By using these, we will find out the unknown reactions of this support. So one is MA, one is RA. We need to find by using this. I will show you how to by using the static equilibrium equation. So summation of all the vertical forces equal to 0. Upward we need to take the positive. So here these two going upward, RA plus 18.09 plus 3.6 is also going upward, and load 20 kilonewton and 12 kilonewton moving downward. We need to take the negative, minus 20 and minus 12 is equal to 0. So by solving, our RA value will come out as 10.26 kilonewton. So it is positive, means the whatever the direction we gave was right. Similarly, we need to find the moment by applying the static equation, that is summation of all the moment is equal to 0. So it is moving anti-clockwise, so negative, so minus MA, and here also this is moving downward no. So we need to take the clockwise reactions positive here. So it is moving like this clockwise. So we need to take positive. Clockwise means we need to take the positive. So 20 into, at a distance of from here to here is 4. And here one reaction, it is moving anti-clockwise. That is anti-clockwise means minus 18.09. At a distance of from here to here is 4 into 4. And plus here one load is moving clockwise, 12 into a distance of from here to here is 12, and here also it is moving anti-clockwise, so minus 3 into 6 is at a distance of from here to here is 16 into 16 is equal to 0. So now we have to solve it. See here, this load is moving at a distance of 8. 4 plus 4 is 8 no, so make it as 8. So now solve it. Our MA will come out as 20.8. So it is 20.8. So this is how we need to find the reaction of the fixed support. So now we'll draw the SFD and BMD diagram for this. I will show how to draw that. Now we'll see the shear force diagram. So for this, we'll see the sign convention for drawing the shear force. So which is going upward, we need to take the positive, and here also this is, both are different. See it carefully. So now see here, RA is going upward, so we need to take positive no? So 10.26, it means it comes here, from here to here, and again here 20 kilonewton is coming downward now. We need to minus, see it, I will show. We need to 10.26 minus, we need to do the 20, so it will come out as minus 9.74. So minus 9.74. So minus means it comes here 9.74. So it is moving upward now. We need to add it plus 18.09. So it will come out as 8.34. It is positive also. So here 12 is moving downward. If you minus that, it will come out as 3.66. So if we again here 3.6 is going upward, if we add it, the answer will come out as, final answer will be 0. It will come out as 0. So this is our SFD. So here SFD diagram. Now we will see the bending moment diagram. For this two bending moment diagram will come. I will show you. So our first diagram will be BMD due to end moments. So our end moments will be nothing but our endpoint, that is point A, point B, point C. So for point A, our moment will be 20.8, what we have calculated, but it is moving anti-clockwise. It means negative. For our bending moment diagram, the negative value should be above the neutral axis. So it means it comes here 20.8. We should negative value also comes above the neutral axis. It comes here. And for point B, we need to find the moment. For that, I will calculate here. For MB, here it is, so it is moving upward now, so we need to take positive now. So it is moving upward, so 3.66 at a distance of, here also 4, here also 4 plus 4, 8. So 3.66 into 8, here 12 kilonewton is there. Now we are calculating the bending moment for this member. We need to only see, we need to hide it, we need to see only this portion. So 12 is there, it is moving downward, so minus 12 into the distance of 4 into 4, so it will come out as minus 19.2. It is also negative, so negative value comes above the neutral axis. So minus 19 means it comes here 19.2. so it also comes here. The diagram will be, it comes like this, and at point C the bending moment will be 0. Why? Because this is the internal hinge, this is the continuous beam. Within the internal beams, at internal hinge the bending moment becomes 0. So it comes like this. So you may ask, this is also simply supported, so why it is not becomes 0? Because the point B is, it is continuing, this is not continuing, it is an internal hinge within the continuous beam. So at this support the moment becomes 0. Here bending moment is not become 0 because the beam is continuing, here it is not. So it comes like this, so it is 0 only, sorry, it is negative only. Now we will see the bending moment due to loads, that is 20 and 12. So for that we have the formula WAB divided by L. For 20 loads, 20 into A is 4, B is 4, divided by length is 8. So it will come out as, for load 20 it will come out as 40. So 40. So for point load the diagram will be, it will come triangle like this, it will come like this. And for this also it will come point load. So the load is 12, no? 12 into A is 4, B is 4, divided by 8. So it will come out as 24. So it will come like this, 24. So bending moment due to load. So now we need to combine these two and draw it here. So it will come like this. So it is positive, this is negative, it is also negative. So if you want you can shade this portion. So this is the net bending moment diagram for this problem. This is how we need to find the, this is how we need to solve the problem by using the flexibility method. I hope you all are understood. So if you like the video, like it, share it and subscribe for the more videos. Thank you for watching.